So, introducing our first speaker, Alexander Titus. I'm going to share my screen and hopefully play his video. Here we go. And Alexander, take it away.
Hi, everyone, and good morning, afternoon, or evening, wherever you happen to be. It's great to be here today. My name is Alexander Titus, and I am part of Google Cloud and part of the global public sector practice. And within the global public sector, I lead our healthcare and sciences strategy, working with governments and universities worldwide on taking advantage of the best that cloud and cloud-based HPC can bring to research and healthcare delivery and things like that. One of the silver linings of us being in a remote session is it's exciting that we can have people from a much wider geographic area. So I'm really glad that everyone's here today. This is a really important topic. I think there's a big emphasis and a huge need, especially given the last 18 months or so and how fast we've been pushing the limits in science, particularly in drug development for COVID. So I'm going to talk a little bit about HPC in a box, which really what I mean by that is how do you take a cloud-based high-performance computer and make it accessible and easy to use in a way that no matter what type of scientific or computing endeavor you're going for, you can access that. And from a Google perspective, it's really focused around the infrastructure that we've built over the last 2+ decades, for products and services that service over 1 billion users each. And so these are all powered by what is Google Cloud. And each and every one of these has users from a wide variety of backgrounds, of use cases. Many of these are on the commercial side or the kind of individual user side, but Google Cloud is really starting to allow research teams, scientists, and in the enterprise to take advantage of this large scale computing that's really, that we've found has been really powerful to bring insights out of data. And, just for a little brief background about Google Cloud, there's over 1 billion unique IP addresses served every day, caching points around the world, and an uptime that is designed to give people really good confidence in the fact that your computing infrastructure is always going to be there when you need it. Whether you're doing, high need, high uptime kind of HPC work, or even on the research side, making sure that you have access to research computing resources when you need them. And as many people here know, and that's the reason we're here having these conversations, is HPCs, being able to leverage these large-scale computing infrastructure, whether it's on-premise or in the cloud, impacts a wide array of industries. Everything from weather. There's in the U.S. there is a lot of wildfires going on right now, for example, and hurricanes, and how best to predict where those are going to happen. To media and what's powering the behind the scenes of modern digital art. But today, because I come from the healthcare and life sciences space, I'm going to talk a little bit more about the healthcare and genomics angle of cloud-based HPC. But again, a lot of these examples in this conversation can really be applied across the board. And so life sciences organizations are really focused on using technology to bring drugs to market faster, whether it's a drug development or a biotech startup, large pharma, or even synthetic biology in the non-drug space. There's a massive amount of data and compute required to tackle these types of industries. So in the 2010s, the US Food and Drug Administration approved more drugs annually on average than it did in the previous decades. So the pace with which we're accelerating drug discovery is in large part to an increased amount of data and an increase in computing power to get more and more granular on a successful precision medicines and precision therapies. And COVID-19 has certainly accelerated the drug discovery process, whether it's therapeutic antibodies or new vaccine technologies. The need to more quickly develop these types of drugs has never been more important, which is why scientists and research teams have started even more so than ever using supercomputers to to run data intensive tests and part of the COVID-19 drug development. But again, that's that can be applied to, same theme can be applied to any type of drug development or technology. And from this big need during COVID-19 was, it became obvious to a number of providers, cloud providers, and leading scientists that there really needs to be a high performance computing consortium to tackle some of the big questions with the SARS coronavirus and COVID-19. And so Google Cloud is a proud partner of one of these, and many of our other partners within the consortium are also here presenting during this symposium. But as you can see just here as a snapshot, over 100 projects have been resourced through this with over 6.8 million CPU cores and thousands of CPU hours processed through here. So the ability to tackle, whether it's modeling, whether it's protein folding, whether it's clinical trials in some capacity, being able to tackle these with high performance computing is a really big part of how we've tried to bring the best of Google to tackle the COVID-19 response. And so increasingly relying on high performance computing for this amount of data is really around, at least in the life sciences, is around analyzing genomic data to get insights into diseases and those therapeutic targets. So not just understanding the underlying disease, but then how do you run computational experiments to actually model the interactions, whether it's biologics or small drugs, to tackle those therapeutic targets. And all of this, again, is focused on accelerating drug discovery to optimize that delivery of pharmaceuticals. One of the challenges to traditional high-performance computing is it can be expensive and sometimes inflexible. So if you see the chart here on the right, oftentimes the total capacity is that kind of horizontal green line. Oftentimes, when you're at capacity, you have to spend quite a bit of time waiting in the queue to be able to access a node or a set of nodes on an HPC. I know when I was in grad school, I spent weeks and weeks waiting in line for my university's research computing cluster before I could get in to run experiments sometimes, which means that when the demand for consumption is greater than your capacity, you have missed opportunity. And then on the flip side, when you have less demand than the capacity you have, then your fixed cost of a traditional research computing core or HPC can then be wasted money, if you will, or cost overrun that you don't necessarily need to use in that moment. So the traditional paradigm is not a directly proportional cost to the need you have at the moment. So the Google Cloud's HPC solutions are really built around exactly those things: reducing time to delivery, paying for only what you need, and making progress faster through these research questions. And so in the reduced time to delivery, an example of a project in a partnership that we have, Schrodinger has been using Google Cloud for COVID-19 drug discovery and has been using it to accelerate the R&D behind some of the calculations for these chemical reactions and the chemical reactivity, and all designed to do pre-screening before having to actually do physical analysis. And so what I see HPC and AI and machine learning applications in general is the ability to triage through the hypotheses, all the questions you could possibly be looking for, and have a more effective choosing of the examples and the experiments you actually run in real life. And so leveraging Google Cloud's purpose-built infrastructure for flexibility, they're able to improve their preclinical drug discovery and actually virtualize a lot of the compound synthesis under looking at how to best predict which are going to be the most effective against targeting with the compounds they have against targeting the kinds of therapeutic targets they're looking at. And then on the theme of paying only for what you need, Google Cloud and the Broad Institute have had a close relationship for a while, and the Broad Institute has been really successful at finding the right way to dynamically scale resources to fuel their research. So on a flexible per second billing instead of a static pre-provisioned resource, the ability to hone in and pay for exactly how much you need when you need it, which is all tied into effortlessly scaling resources, but then wrapping up and turning off those resources when you're no longer using them. And a lot of that is built in around a fully managed service that goes along with many of the cloud-based HPC tools. And so then scientists can not spend as much time worrying about actually launching Cloud HPC or not, but can focus on doing the analysis, reducing, you see here, the analyzing genomes 4x faster compared to on-site computing clusters. The Broad Institute produces terabytes and terabytes of data a day, so the ability to compute that at scale is really important. And then another focus on the innovate more rapidly. USC and Google Cloud have worked together, and USC has used Google Cloud to screen almost 700 million chemical compounds in 24 hours to combat opioid addiction. So while much of what I've talked about so far has been around COVID-19, these same applications will extend to other targets. And so how to use automated tools, templated configurations to scale up and deploy an HPC that would then allow the USC team to take advantage of more advanced machine learning. So again, this is kind of the HPC in a box theme, where being able to take templated configurations, launch tools, and take advantage of built-in machine learning models helps to then integrate with the other more domain-specific solutions like genomic analysis, collecting real-world data through clinical trials to compare to the success of those predictions. And over the course of this example, narrowing down nearly 700 million compounds to 120 promising candidates for testing. So again, that's the hypothesis triage, the ability to do this at scale in really a relatively short amount of time enables that to happen. And all of this, I mentioned at the beginning, where Google comes to this perspective from large-scale enterprise and the products that serve over 1 billion users, but we also like to think of it as a one Google or even a one Alphabet approach to science and research and to bringing HPC to specific domains. So if you see here on the right side, Verily Life Sciences and Calico are focused on the life sciences world. Google X is really focused on pushing the limits on a number of different kind of emerging areas. Waymo, self-driving cars, the amount of compute that goes into processing all the sensor information that comes from running self-driving cars is really huge. And even with GB and capital G, these are investment arms where we deeply understand the need of small startups and rapidly growing startups and small enterprises to be able to get the value out of their high performance computing without overpaying or overextending themselves early on. And so scaling resources as a company grows is something that's deeply built into everything that we focus on. And a lot of this is possible by bringing the best of HPC, or the best of enterprise technology to the HPC. So first and foremost is top of mind for a lot of people right now is best-in-class security. So how do you have full control and privacy of your data while being HIPAA compliant or whatever else, any other types of privacy and security controls you'd like to play in there. And we really take an approach to a multi-cloud, hybrid cloud environment. So research computing infrastructure that is either at your university or at your institution or your company is really valuable resources. So how do you best pair a hybrid approach where you have cloud-based HPC with an on-premise solution, and then even potentially with any other cloud environments that you're working with? So how do you develop once and then access from everywhere? And that is all built around the goal of leveraging big data and then applying models that are particularly well designed for large data sets. And in this case, this example, right, AI and machine learning does really well. These algorithms do really well once you start to have large amounts of data overall. And then, of course, the one Google, as I just mentioned, is really a core theme of what we do in everything we do. And then a commitment to sustainability. So Google Cloud is 100% renewable energy and zero net carbon emissions. So this means that every time you run an HPC workload in Google Cloud, it's an environmentally responsible thing to do because you're not producing more emissions, right? You're breaking even, and so it helps have a more environmentally environmental focus on computing, because large scale compute is a large consumer of energy worldwide. So how do we best make sure that we're being responsible as we're increasing the amount of storage and compute that's going on in all of this architecture? And so for one last example here, I want to highlight another COVID application using some of the HPC capabilities in cloud. Collaboration between Google Cloud and a team at Harvard, developing an open source virtual drug screening platform called Virtual Flow. And so the team at Harvard was able to screen 1.4 billion compounds in 5 days. So the speed with which you could screen through billions of potential possibilities is really a powerful enabler, or powerfully enabled by the cloud, using, in this case, 80,000 CPUs and 750 million CPU hours. And then again, the whole idea is, like I said before, bringing these down to a targeted set of hypotheses. So in this case, 16 proteins that they can perform screening and actual physical characterization of. And as you can see here, being able to screen 1.4 billion compounds now gives us hope for being able to screen 10, 20, 30 billion compounds in the future, and ideally rapidly kind of changing the way we do drug discovery to make that a faster process, in the preparation for the next pandemic or whatever else big precision medical challenges we're trying to tackle. So really, HPC in a box here is the concept of providing best in class to people who need to use it, to scientists and research teams who are trying to take advantage of large scale compute. And so this, like I said, from that kind of a hybrid approach, really one way to think about this is if you have a fixed set of on-prem resources, a great way to pair in a hybrid manner with cloud-based HPC is effectively bursting onto the cloud when that resource demand is larger than the resource capacity. And this is done through a number of open source schedulers that people are likely familiar with, Slurm, Torque, and what have you, but still maintaining, even when you're bursting off of your on-premise technology into the cloud, how do you maintain that security, auditability, and compliance? So when you're sharing that data externally, quote unquote, from your local environment to a cloud-based environment, how do you make sure you have that high quality enterprise security throughout? And again, that allows to then have, you only pay for the resources when you need them, so the volume you need. And then in the events you can predict how much you're going to need, then there are also ability to do subscription-based pricing as well. But pairing that with the ability to put self-service dashboards onto cloud resource management, research results, all tied together is a great way to focus on how to tackle and how to best use kind of a hybrid approach in that kind of HPC in a box theme, if you will. So that's where I'm going to wrap up, and I'm going to end my time here. I appreciate everyone joining. I think there's going to be time for questions later, so I'm looking forward to having a conversation. If anyone would like to chat, get in touch. My email is at the beginning of this, but it is alexandertitus@google.com. And you can learn more about our Google's HPC resources at cloud.google.com/HPC. And I appreciate everyone's time and looking forward to chatting with you more soon.
Thank you very much for that talk, Titus. Hope it wasn't too bad watching yourself. I think you did well. So it's time for one quick question now, and then before we move on, does anyone want to pose something? I think Brent had something. Do you want to?
Yeah,
say that,
absolutely. Brent, do you want me to read it? Do you want to chat a bit about your question, a bit of context, your question?
Well, kind of two questions. The first one is, how specific are the hardware offerings? Are they specific down to the application, like a particular offering of a GPU for a particular application? And the second one is kind of the gestalt of all this. Do the users see value predominantly from the reduced queue wait times? Is that where we're seeing all of the value at this point, or is it really down to that hardware level?
Yeah, so I actually think they're tied together as well. So we do quite a bit of what we call solution development. So the underlying hardware components are not necessarily in most cases tailored to specific applications, but the architectures with which we bring together those hardware, that underlying hardware, we do develop solutions that are specific to applications. And that would be, and there's a couple caveats to that. In Google Cloud in particular, we have what's called a tensor processing unit, TPU, which is an even more specialized tool for AI/ML types of capabilities. And so that is a hardware that is more specialized towards those advanced computing. But overall, the architecture is how we pull together those components can be kind of topic specific. And that also then ties into your question about kind of the core value proposition. And when you're not using, so TPUs, there are more resource limited, but when you're using traditional CPUs or GPUs, the ability to scale. So yes, near infinite scale in terms of how many core hours you can use.
Perhaps we'll move on and now let's see, we're going to, our next speaker is Brent Gorda, who just asked a question, Senior Director of High Performance and let's take it away. Except that's right, we'll see what it says in your video. Although my internet connection is currently unstable, let's hope we can make it work. Here we go.
Hi, I'm Brent Gorda, and I'm the Senior Director for High Performance Computing here at ARM. I run a worldwide sales organization focused on high performance computing for the ARM architecture and ecosystem. And as you'll see a little bit more deeper into the software layers of the stack. My background has been in high performance computing for several decades now. I've got a long history with the US Department of Energy starting in the early 90s. I have worked at both Intel and now ARM in a capacity focused on high performance computing and have traveled extensively throughout the world talking to different geographies and organizations about new projects. Until COVID, we were spending a great deal of time outside the US focused on upcoming high performance computing silicon projects. Some of the projects that I've had the joy of working on include the attack of the killer micros, which was a project at the Lawrence Livermore National Laboratory, wherein we studied the microprocessor running in parallel. At that point, massively parallel meant 127 CPUs, to pit that against the vector systems. And out of that grew a very intense focus on parallel computing at the labs. I also worked on the Blue Gene project at Livermore, where we took parallelism from 1,000, 10,000 to 100,000 and then millions of cores, threads of parallel for the applications users to take a look at. I've also done a number of startups along the way. The one that is most relevant to high performance computing was a company called WAMCloud, which focused on the Lustre technology software and preserving that for the high performance computing community. In selling that company to Intel is when I moved on to work at Intel in high performance data division. I've also worked on projects such as the student cluster competition, software carpentry. So I've been involved in quite a few projects that arguably are disruptive to the way business is traditionally done. And that's kind of where I find my element. And that is, in fact, what has brought me to ARM, because there's some technology shifts going on, and I'm excited to be involved in them. I want to speak to you today about the rise of cloud-based high-performance computing. The crib notes here are that I hope to get you to the point of agreement that CPU design and system architecture are cool again. It appears to me that we're exiting the era of only x86 systems available for high-performance computing, and I find that to be transformational and exciting, and so I'm very excited to be here. Starting with, the landscape is maturing for high-performance computing and cloud computing. And I'll get to why these things overlap, but there's a new architecture, #1 on the top 500. And as you can see from the image on the right, that is the A64FX processor, which is a Fujitsu design, soup to nuts with the ARM ISA sitting on top of it. It has been #1 the last 3 lists and took quite a big step forward with respect to performance as well as architecture, because it is a pure CPU. It's not an accelerated CPU. Yes, it's got the SVE vector instructions, the wide vector units on it, and high bandwidth memory, both of which serve to really make this CPU sing. There was another bit of news recently. There was a mainstream high performance computing procurement that was awarded to Azure, which everybody looks at and says that's a cloud company. That's for a traditional HPC application. So there's some interesting activities going on in cloud in HPC. Where the two of them meet, really, we need to focus on what is the convergence of software, and then what's going on underneath in the hardware that makes us so excited and interesting. And then I'll end with what is the impact, what is the opportunity? And in there, I'll talk about, what are the metrics that we care about? The architecture is in transition. What are the metrics we should be watching, and how do they matter to us? There is obviously a big shift in influence for next generation silicon, with the hyperscalers having such spending power, and their interests are directing a whole lot of the attention. And I would add that the hyperscalers actually do care about high performance computing. If you take a look at some of the talent that they've acquired recently, it's pretty clear that their interest in high performance computing is genuine. So what is HPC in the cloud? There's a broad spectrum here, and I want to just give you a 20,000-foot view of my impression. We've got the HPC data center with clusters. We've got the cloud data centers, which are building up infrastructure that run HPC applications. And we've even got the HPC at the edge. 5G is really transforming the ability to move data back and forth. And edge computing is making it possible to do HPC applications on the edge of pretty reasonable capability and scale. So in your HPC data center, cloud companies are showing up, such as AWS Outpost and the new offering from HPE, which is GreenLake, that Max Alt is running right now. Those are very interesting capabilities, effectively managed services on-prem for you to take advantage of high performance computing when it needs to be local. And of course, there's a dozen reasons why having that local to you is worthwhile and even important or critical in terms of where the data lay and that sort of thing. We've got these HPC traditional systems that are looking a lot like cloud. I mentioned the Azure win at the Met Office in the UK. That's a very interesting win. But if you look deep into it, it's a Cray system underneath. And so it looks like a standard HPC system. So you might argue that this is just co-location, but being managed by a cloud company and increasing their capabilities and reach, I think is quite interesting to everyone. And then the other one here that a lot of people probably don't know about is the powered by Fugaku. Fugaku is currently the #1 system on the top 500. And in looking about and reaching into the future, Satoshi and the folks at the Riken Computing Center have carved off a piece of Fugaku and made it available to cloud customers through a channel of 6 or 7 cloud companies in Japan. So Fugaku looks a whole lot like a cloud in that environment. You as an end user business can go run on Fugaku with this infrastructure that they've got in place. One that's really interesting to me and one that we've been following quite closely is this C-Spot project at UC Santa Barbara. And this project is done by Dr. Krintz and Dr. Wolski of Eucalyptus fame. And what this is a serverless platform of things, which is where the Spot comes from. They are out in the citrus groves in the Central Valley of California. the citrus groves are covered in nets, and they're looking to model via CFD applications the wind flow and the temperature deltas in these enclosed areas for the citrus. And they're doing that so they can spray pesticides and nutrients onto the trees, taking into effect the wind and all sorts of issues that get caused by spray and temperature and wind mixing there. What's interesting here is that while they're out there doing this work, they are disconnected from the internet for the most part. They're too far away for that data to make it back to the cloud for any sort of real-time control. So they're doing that at the edge. They're running CFD. They honestly don't really care what the hardware looks like. They can run on anything. They're using the Eucalyptus software, and they're running effectively a cloud and transactional interactions with the CFD apps to help do effectively a real-time control of the spray for those devices. That one is interesting on a number of matters. Now, and then of course, what I think everybody thinks of as cloud is AWS, is Azure, is Google Cloud, all of these that are honestly taking a deep look at high performance computing. Of course, at ARM, we love to pull your attention towards the AWS Graviton and Graviton 2 processors, because they are instances of ARM architecture growing rapidly in the cloud. The processor that I think is worth looking at right now is not an HPC processor. It is the Graviton 2, which is from our N1 IP line. And I think I have a slide on that a little bit later. But it is a data center processor, and AWS is pushing it towards HPC, and HPC is lapping it up because it performs really quite well in their environment. So what is HPC in the cloud? It's just somebody else's computer with managed services on it. I think we've all heard that for the past 10 years. Somewhere the bills need to get paid, and somewhere the rubber hits the road with respect to what software is on it and what's running, how you access it. So really what the question is, it's got to be more expensive, right? Because you're paying for somebody else to stand up a system. And then what does the hardware and what does the software really look like? The software stories is quite mature and interesting in the sense that all of the systems level stuff is pretty much in place and working. And for the most part, it's working the way the traditional HPC applications expect it to work. You've got your standard OS releases, a couple of the new ones with Rocky and Alma coming up. You've got Slurm PBS Pro, you've got your schedulers, you've got the InfiniBand, you've got the runtime libraries, you've got Lustre available, all of that sort of stuff is rapidly maturing and just expected to be there. So all that's kind of fine. The applications are growing leaps and bounds. The open source applications are almost always available on the clouds that we access and performing quite well. I've got a slide here on performance. Where the hockey puck is right now is ISV applications. The ISVs have been standing back looking at the cloud business model and are starting to jump in. And I'd like to argue that a lot of that is due to what AWS is doing with the Graviton 2, and I'll show you some numbers with that. But there's a little bit of a gap here with respect to the workflow and the way the traditional cloud workflow works versus the way HPC works. So I'd like to draw your attention to a group, HPCNG, I believe it's .org, which is a newly formed group that's working on trying to steer those two groups together such that the workflows and the tools and the practices will converge at some point in the future, such that you'll be using the same infrastructure on your on-prem HPC system as you might in the cloud, and making it easier for end users to take advantage of things. So that's the software. On the hardware side, remember, it's just somebody else's computer. We've kind of got three things that we want to talk about. We've got the network, we've got the storage, we've got the processing. So as Sun used to say, the network is the computer. And frankly, most cloud offerings have come up short here. And that's where I think a lot of the pushback from the traditional HPC community has been. Latencies are too high, bandwidths are too low, noisy neighbor problems, all that make it pretty much untractable for the applications that traditionally constitute the high end of HPC, this distributed linear algebra workloads. But clearly that's not the case for these dense neural network algorithms that the clouds are taking advantage of, and they're pushing quite hard in that area. So there's a little bit of a divergence in terms of what HPC means on both sides, but they are converging, and there's an opportunity here to get workloads included in the mix for next generation of silicon. And of course, there's some exceptions. Like I said, the Azure win with the UK Met Office is a full-on Cray system, I believe, with AMD processors. And so that may be co-locating, but still available in the right environment for you. Storage has come a long way. The cloud companies clearly have hired much of the Lustre talent. They've got BGFS offering, they've got Ceph. They're more coming as they are a step or two ahead of the HPC community with respect to object store. But with Deos and with Project Red, I think the HPC community is rapidly catching up there. Again, where I'll draw your attention is the processor architecture. Where's the puck going? Where should we be skating to here? And from my point of view, ARM is where a lot of this activity is happening. There's some going on in the RISC-V community as well. Our experience with ARM is that it just works. It works in production. And if you own your source code, you can just type make and run. With some of the software offerings like SPAC, you're finding that the ARM architecture is just supported from the ground up. You can get a support contract from Red Hat. You can get a support contract even from LambCloud to support your ARM clients to a Lustre file system. So my argument here is that ARM just works, and it's growing in capability and performance to be on par with the best of x86. So really, what's your metric? Is it Bogle MIPS? Is it some sort of peak floating point operation, or is it something? Step back from there and think about time to solution. If you include both the runtime and the queue weights, I think the cloud has a bit of an advantage here, where oftentimes the queue weights are fairly small and your runtime is on par, and you find that your turnaround time is better. And so the cost might be, the price to solution might be the metric to focus on here, as well as the time to solution. And then acquisition and operating costs, of course, factor in as the big widget here. So we took a look at this is the Ultra, the Ampere Ultra processor, and compared that to, I believe it's an AMD processor. It's the best of the best on both sides, where the x86 processor is the one line, and what you see across a handful of 20 or so apps that it's about on par. So the best current ARM offering from Ampere is about on par with the best AMD offering, neither of which are purely focused on high performance computing. If you had the Fujitsu processor in here, it might be less of an equal measurement. When you add in the GPU accelerations, you find pretty much the same thing. Across the board, the ARM processor and the x86 processor perform roughly equally. These are clearly bounded by the performance of the GPU and the IO bandwidth between the processor and the GPU. So when you make those about even, you get performance that's about even, no secret there. A lot of the processing on the GPUs, in fact, is gated by the performance of the CPU. And so you'll find that this will be an interesting place to watch. by changing the metric, if you take a look at the middle graph here, where it's the cost per simulation run, you'll find the cost to be about 40% cheaper on ARM than on x86. So on the left, you'll see that the runtime is different. That's 6.5 hours, maybe 6.75 hours. So it's different by 10 or 15 minutes. Your cost is cheaper by 40%. It's a trade-off most people are willing to make. With the ARM environment, we provide IP that spans the globe from IoT through the networking and the edge, all the way up to the data center and to HPC on the far left. These are the ARM Neoverse IP cores that are available to our customers. So I see I'm right at the mark here. The ability to influence silicon design right now is quite high. It's in flux. The hyperscalers are taking a very close look at alternatives. ARM is the current choice right now. There's other architectures such as the RISC-V architecture that others are looking on. I think it's a good time to be doing architecture research and especially silicon design. Our researchers are very focused on next generation features that increase the performance of the ARM IP. The cloud companies have HPC interests, both in their own AI ML workloads and in the broader HPC workloads. So they're taking advantage of their growing infrastructure to serve our market. And as the folks at Hyperion say, that is additive to the HPC market. So it's a great thing growing HPC demand and use of the stuff that we've been working on for the past 20 years. So there's an advantage in scale, and there's an advantage in the variety of hardware that the cloud companies are able to provide to their customers. This is very complementary to traditional HPC. The tightly coupled applications that are dependent on the low latency, low noise environments still need a tight network to work on. The leadership class computing. At the DOE, we had advanced architectures as a class, which are the blue gene type architectures, followed by the capability systems, which are the top 10 hero systems, the new exascale platforms that are being installed right now, and the capacity systems, which are your day-to-day run thousands of jobs over thousands of parameters kind of clusters. Hyperscalers are clearly offering solutions in that last category in the capacity category. And by partnering with them, I think the high performance computing community, the HPC among us, would do well. So in conclusion, thank you for joining me today.
Thank you very much. There's time for a quick question while I switch our displays. Anyone want to raise, make a comment or answer a question? Otherwise, I'm bringing up our next video.
Looks like my typing is keeping up with demand.
Yeah.
Good afternoon. My
Yep.
name is
How are we doing? Any questions, or shall I just get us going? Maybe I should get us going. Let me share the screen.
I think there's an interesting point worth reiterating that Brent came up with, and that the A64FX compares well to a GPU on heavy workloads when it comes to using a CPU core architecture versus GPUs. I think that's, if the costs are correct, that's probably a very disruptive technology to think about.
HBM plus the vector units with gather scatter, those sorts of capabilities.
Right.
Just raises the bar. Most applications are starved on memory, and they just kick that up to GPU class memory performance. That does a lot.
Interesting. Okay. Well, let me now move on to our third talk. Steve Hebert, I think it's pronounced. He's the Vice President, Global Head of HPC Cloud at Atos Nibix. He's actually in Paris today, so he's represented here by Leo, but we'll listen to his recorded talk, but you can ask all your hard questions of Leo once we're done. So let's go.
Good afternoon. My name is Steve Hebert, and I'm one of the founders of Nibix. And today I'm going to be focusing my talk around the evolution and advances in hybrid cloud HPC workflows, leveraging the most capable classes of infrastructure where they are available, whether that be using on-prem supercomputers or leveraging cloud computing infrastructure. And I think as part of the IEEE Symposium on Cloud HPC, you're going to hear a lot about what's available to support HPC workloads in public cloud. But I think having worked in this field for the last decade, I think what I want to focus my presentation on is the next evolution of HPC, which includes both cloud resources as well as the latest technology in on-prem supercomputers. To give you a little bit of background about Nibix and our history in HPC in the cloud, Nibix was actually founded to deliver true HPC and supercomputing class resources in the cloud. And I think importantly, Nibix also sought to usher in the era of accelerated computing. And we launched this, we called it NAC, the Nibix Accelerated Compute Cloud, over 10 years ago. And it was a pure play HPC cloud service that focused on accelerated software applications using next generation infrastructure technology. And at this time, obviously, in the hyperscale public clouds, there simply wasn't typically the type of resources available, and certainly not at attractive economics, to do what most people considered real HPC work. Now, a lot has changed in the last decade, and just following the evolution of Nibix through this time, we developed a platform technology in 2013 that we called Jarvis. And this was really the first container native HPC cloud platform. And the reason Nibix developed our technology around containers was to provide the same level of agility for cloud resources as our virtual machine counterparts at the traditional public cloud platform providers. And I think the goal here is to really provide both software as a service for domain experts, as well as a platform for those developers that were building next generation applications. And if we follow that through in 2018, we actually began licensing Jarvis XC as a platform software product to enable hybrid cloud HPC. I'll talk a little bit more about that later in the presentation. And then obviously, importantly, part of this and the whole idea around high performance computing in general is it ultimately revolves around domain applications. And this is where HyperHub, which is the curation of these applications for HPC and accelerated computing, being click to run and runnable anywhere over time. And then actually in 2021, earlier this year, Nibix was acquired by Atos, which is one of the leading supercomputing OEMs in the world, so that we can, of course, blend for our customers both a cloud computing and hybrid cloud platform, pairing that with best in breed state-of-the-art infrastructure for on-prem supercomputers. So let's talk a little bit about what are the drivers behind both cloud, the consumption of cloud resources for HPC, as well as just the traditional market drivers of next generation technology. And really this comes as no surprise to most of you. It's around data processing and data transformation at massive, massive scale. We have many devices, sensors, compute platforms that are generating data that needs to be analyzed and or transformed. And I use the terms analyze and transform very broadly because as most of us in HPC know, transformations may be actual computation using advanced physics solvers and parallel processing for scaling out applications and those solvers over time. But this also is broadened to include things like streaming data, high throughput computing, where you're transforming data inline, en route as it's being processed. And ultimately, the goal is to drive results, knowledge, and services as outputs to this process and this data processing platform. And of course, this is driving an acceleration of the demands for computation. So it's not just linear growth anymore. And for those of you who've been in the HPC business a long time and have tracked, server shipments and application evolution over time, this, shouldn't come as a big surprise that with the growth and proliferation of that data, there's simply more computation that we need to do. Furthermore, our models, the types of products that we're developing are actually getting more complex, finer grained meshes, which ultimately increase exponentially the computational processing power needed to satisfy those demands. So we're also now finding that traditional on-prem supercomputers are one element of the solution. And obviously we continue to invest in the latest capabilities down to the silicon to deliver those capabilities, but also now the promise of the massive availability of compute around the world in cloud. Certainly, obviously, as enterprises are adding new workloads, they're less dependent on a single domain and actually oftentimes have multiple domains which have extraordinary computational demands. And certainly these are getting increasingly complex to consume over time. And so this is really an industry challenge. And I think what you'll see thematically through other presentations today is the need, and obviously these are the drivers behind the consumption of HPC in the cloud. However, it's not as simple as forklifting workloads from a supercomputer to the cloud, and increasingly HPC applications require, certainly oftentimes prefer, different architectures. And oftentimes developers are having to force their applications into a given architecture because it's what's available. For example, traditional HPC cloud was historically virtual CPUs, cores, and memory, and maybe some fast storage. But as we look at the evolution of workloads, there are many different available hardware capabilities to actually increase the throughput and computational efficiency of these workloads. So if we think about this in two columns, really application domains being what the domain scientists, engineers, et cetera, may be using to conduct their science, whether it's in life sciences with next generation sequencing, whether you're a data scientist doing deep learning, both training and inference, and oftentimes the infrastructure for training and inference may be different. Or if you're developing traditional physics-based solvers in-house for your domains, the compute requirements for these applications can be very different. And we certainly have developed massive amounts of legacy code around the x86 architecture. We've seen a huge evolution over the last decade to the deployment of CUDA for GPU accelerated computing, but also now increasingly, and you'll hear today from folks from ARM about the evolution of ARM processors in HPC. You're hearing more about RISC-V, FPGA accelerators, streaming processors, and AI engines for very domain-specific computing. And this is obviously extremely important when we look to increase power efficiency and throughput to chug through our data. And then all of the ancillary compute elements that are needed to actually process the information. Different types of memory, different types of actual operations, whether it's single precision, double precision, low latency interconnects, which has often been a challenge when moving workloads, especially massively parallel workloads, to the cloud, where the solvers rely on very fast and low latency interconnect. So this is, again, yet another trend driving not just consumption in the cloud generically, but heterogeneity in our state-of-the-art compute resources. One of the other essential components for the adoption of HPC cloud is working to modernize the application deployment, not just for, in general, data for application migration, but for the ability to take advantage of accelerated hardware where it's available. And so these apps increasingly need to be adaptable and available at any point on various infrastructures simultaneously. And this is where you'll see, obviously, a lot going on around the adoption of containers, containerized HPC, which Nibix pioneered back all the way in 2013, which also allows the applications to take advantage of the capabilities of the hardware, whether it's passing through InfiniBand fabric or any low latency hardware interconnect, whether it's passing in FPGA accelerators, GPUs, et cetera. All of these can be adapted in a containerized application environments, which makes them portable, much like an app store does for moving your applications across various mobile devices. Now you can do the same thing across HPC infrastructures. So thinking through then what this means for hybrid on-prem and cloud workflows for HPC in general. So think about from the point of view of the domain scientists, there are maybe multiple compute endpoints, an on-prem supercomputer, but the need or requirement to burst or move certain workloads to the cloud. For example, if a latest generation supercomputer was an x86 based supercomputer, but there were perhaps workloads that could benefit or leveraged the ARM CPU as one workload type, being able to take advantage of that application on a cloud endpoint that avails those ARM processors becomes really important. And it enables organizations to balance and optimize both for economics and performance between different compute resources and infrastructures. It also, importantly, you want to be able to preserve existing applications and workflows that are the engineers and domain scientists are consistently using, and without having to forklift or change those workflows simply to adapt to something in the cloud or a hybrid workflow. And so in effect, obviously limiting customizations for any specific infrastructure. You want to actually maintain a platform level consistency irrespective of it. And then ultimately this leads to optimizations where you can drive computing based on policy, have visibility across all resources, applications, machines, and users globally. So let's talk a little bit about a hybrid or multi-cloud architecture. And when I say multi-cloud architecture, it doesn't necessarily have to mean that you're deploying work on an Amazon or a Microsoft and a Google and an IBM or Oracle or any of the hyperscale clouds. It can also be a hybrid or multi-cloud from within multiple in-house data centers, any down compute endpoint. And Nibix uses the terms upstream and downstream to really think through the architecture of what a hybrid HPC platform looks like. And on the upstream side, this is really, think of it as the control plane where you have authentication, where end users are basically maintained, and the actual architecture is landscaped from a multi-cluster and multi-zoning standpoint, along with a processing API, and then certainly and importantly, as I just mentioned, managing and deploying the applications and the synchronization of those apps and workflows in a point-and-click way to any compute endpoint. And then those compute endpoints are the downstream federated endpoints. And these can be federated by both compute and storage, because importantly, compute and data need to coexist. And so part of the architecture in a hybrid multi-cloud landscape is, of course, really thinking through the data how data is federated, data may be regulated, and policies around data governance are going to be really important. But ultimately, this enables unlimited compute endpoints on any class of infrastructure with any type of device or devices or architectures in those compute infrastructures, whether you have downstreams that have GPUs or FPGAs or fast fabric or any type of topology that may be needed for the given application domain. And then the thought here is about using Kubernetes compatible infrastructure to support converged federation, converging on modern infrastructure as code technology that bridges traditional HPC with modern deep learning, AI, and data center infrastructure technologies to create a unified platform, infrastructure platform, which, again, focuses on minimal, configuration on the downstream platforms. So a little bit about HPC on Kubernetes. And Nibix is one of the first organizations in the world to actually rethink HPC scheduling across heterogeneous multi-compute endpoints. And if we think about traditional HPC, when workload managers and schedulers such as Slurm, LSF, SunGridIGM, which are fantastic tools, and most of us have used them for years. Nibix ourselves had deployed variants of these in the Nibix cloud. But as we thought through next generation HPC, and we look at the proliferation of things and tools like Kubernetes, and thinking about the future of HPC with heterogeneity, is how do we enable a seamless connection of multiple infrastructures, but drive advanced scheduling technologies to move across federated compute endpoints. And so this gives a bit of an architectural view of how Nibix has tackled, the HPC scheduling challenge. We could do a whole nother talk on HPC on Kubernetes, and there is a great white paper that Leo Reiter, the Nibix CTO, has written. You can download it from the Nibix website if you have interest in this. Certainly, it sparks a lot of academic discussion around scheduling, since a lot of different clouds and cloud providers may support various interfaces to traditional workload managers and schedulers. Those are all great tools when we look at hybrid cloud. This is simply another way of thinking about how HPC can be done. And the Nibix platform for doing this is Jarvis XE, but importantly, irrespective of the Jarvis elements, really the idea of hybrid cloud HPC workflows, there are a number of key elements that would be required to really think through how this can be deployed seamlessly across multiple endpoints. And obviously, importantly, as I mentioned, there's the user interface, a core API, and in the sort of the management and control plane infrastructure. There's a lot of tools and capabilities packed into this, and the whole idea here is to provide global visibility to admins for HPC, team leads, domain scientists, corporate IT, to be able to manage the landscape. The other important and key component is the HPC scheduling technology, and being able to use some of the elements that have been developed over many years from traditional schedulers, but being able to adapt those to a web services scheduling technology platform like Kubernetes, but be able to adapt it to the HPC use cases, which is precisely what Nibix has deployed in our Jarvis platform. The other component is creating deployment automation for this, making the creation of these upstream and downstream endpoints completely seamless and completely non-disruptive. And one of the things that's really fascinating, if you're an HPC admin, is to think about if your scheduler goes down or a section of your cluster goes down where you're disrupting workloads. In this type of scenario, you can actually do seamless updates to both upstream and downstream compute workers without disrupting a single job that's running. And this is possible because of the containerization and the way that the technology is deployed in the upstream downstream architecture to enable the code itself to be updated, the platform code, without actually disrupting the applications that are currently running on the infrastructure. And then finally, and importantly for hybrid workflows, is you want to have the quote unquote app store or the application catalog. And Nibix deploys a catalog. It's really a meta catalog called HyperHub. It's includes a lot of mainstream and commercial solvers and applications, but it's also a platform that enables customers and developers to deploy their own algorithms and applications as a platform option for continuous integration and continuous deployment. And when thinking through the elements of a hybrid cloud workflow is this idea that when I deploy an update to my app, and it may be an MPI app, it may be a new version of OpenFOAM, how do I ensure and have that propagate seamlessly and invisibly to every compute endpoint, whether it's running in the cloud or on-prem? And that's precisely what a hybrid cloud technology platform should be enabling. And then ultimately, it's a lift and shift from to hybrid cloud and multi-cloud HPC, but importantly, providing the portability for legacy workflows and getting the benefits of this. So whether you're currently using Slurm, SGE, LSF, creating the compatibility to the modern APIs that allow the interfacing to these new types of capabilities and the new classes of infrastructure coming online at various providers and through various on-prem deployments around the world. Finally, thinking about attributes and considerations for next generation hybrid HPC. And obviously important to HPC has always been performance, and we're constantly building new capability machines, but certainly for given organizations, there's other considerations besides performance. There's ease of use, time to deployment, the addition of accelerators. Does your on-prem cluster have FPGAs? Does it have GPUs? Does it have new AI chips? And if not, that's okay. There may be compute endpoints in the cloud that have these tools available. And so it is possible to do it yourself in the cloud HPC. It's possible to do it yourself with in-house HPC and traditional schedulers. But thinking through some of the core attributes for your use cases and domain users is going to be really important as we look into the next 5 years of HPC. With that, I'd like to thank you for your time and thank the program chairs for giving me the opportunity to speak with you today. And welcome any questions you may have. My contact information is below for your reference. Thank you again.
Well, I'll say thank you to Steve, although he's not here in person, but Leo Reiter, his colleague, is. So at this point, we can certainly pose questions to Leo or to anyone else who, I see Brent is still with us. Any questions people may have?
So Leo, we try to make the argument that ARM just works and that the architecture is shifting. Does that resonate with you folks? Do you see more alternatives to x86 in the future? And what's the magnitude of that change? Is it going to be 10% in 5 years? Is it going to be 50% in 5 years or somewhere in between?
I mean, I can't predict that, but as far as the magnitude goes, but in terms of the interest, definitely the whole Recon experience for us and porting our software to the ARM architecture was very seamless, as you would expect. And we had a great experience with Recon with the FX700 systems there, and that's actually kind of teed up a lot of interest commercially on our end. I think the issue, so we are working with customers and partners that are ARM specific, which was not happening a year or two ago, which is fantastic to see. I think the one thing I would say from our perspective, because we are a software and a software as a service company, is that when it comes to people licensing our software, they come to us with an actual infrastructure they want to deploy it on, typically. The cloud changes that significantly, and there's a lot of customers that have interest in kind of forward-looking stuff, like they want to see how these algorithms work on the ARM systems, and they can use Graviton very easily for that. I think your point about the puck being in the ISV's court is very important. Applications are what's going to pull this ultimately, I think, and some of these applications are incredibly sticky. So once that happens, and once you have a price performance advantage, I feel like that's going to be it's going to be just something that continues to pay off long term. So I would say that that's your challenge to really convince the ISVs that they need to do more to support the architecture. I do agree that it just works. There's no question about that. It works very well, and system software support is spot on. So there's just no issue there whatsoever.
Yeah. So the other one, Ian, I'll try to drag you in on this one, is I think we're teeing up an argument here for accelerated workloads versus traditional CPU, right? Obviously, Fugaku shows that you can put a pretty significant number of flops down on a CPU and feed it with HBM and SVE and so on. But if you stand back and take a look at the landscape, there's a lot of effort going into acceleration with GPUs and Intel's new offering, NVIDIA and so on. Do you see this being a long-term battle? Do you think it just goes all one way or the other? Both you guys, what's your sense of?
Yeah, that's a really interesting question. I was initially very discouraged when GPUs arrived. I thought, my God, now we're going to have these horrible heterogeneous systems. But I figured that they would eventually reintegrate in some way. And so I don't know, is your what's it called? The F64 FX system, does that represent one step towards that reintegration, or is it not going to happen? I'd be very interested in people's opinion.
Leo, do you have an opinion on that?
So like I asked earlier, the question I asked about kind of a price performance comparison on those cores versus GPU cores that's specific to a commercial opportunity we're working on right now. So it's actually really contextual, really interesting. We've always been, to quote Steve, and he didn't say this in his presentation, but we've always been Switzerland in this respect. We enable whatever infrastructure our customers want to use, and for whatever use case, and all of the above. And that's when we did operate our own data centers, which we actually switched to using public cloud a few months ago. But for many years we operated our own data centers. We had all kinds of stuff. We had GPUs, we had FPGAs. We had at one point we had DSPs in our systems that were being used by some customers. And then of course, between x86 and at the time Power cores. So it was really just application and customer driven. Our vision is that it's going to coexist. It's not really, GPUs can't do everything and never will be able to do everything. So I personally think that it's good for NVIDIA to have competition on the GPU front, especially. So that's my opinion, but I think that's good for the market in general.
But if you have this mix of FPGAs and GPUs and CPUs, it's less likely to just work, right? Then that's
and for our thesis has always been that software enables the sort of the brokering and the is the traffic cop when it comes to figuring out which applications work with what. Otherwise, end users who are trying to get work done, not just experimenting, have a pretty hard time choosing or lining up applications with specific resources. So we've always been focused on that, on the actual resource provisioning side for whatever the application, whatever makes sense. So we're happy in a world where they coexist, indefinitely.
Do our other listeners have any question they'd like to ask? Otherwise we're getting to the end of our time, actually, sadly. It's a nice thing about having pre-recorded talks is you don't need to worry about people running long when they're speaking, but nevertheless, we managed to use up all the time with relatively little time for Q&A. But it was 3 very interesting talks and certainly given me things to think about, and I hope others as well. I'm going to go out and follow up on several of the issues that were raised here. So thanks again to all the speakers and to Leo for joining us as a stand-in, a very knowledgeable respondent to questions. So thanks everyone. Oh yes, so and Yongshan is, but people are realizing that we can do a clap if we put it at the bottom. That's good. So let's see if I can do that. There I am. Yep, clapping. So thanks everyone for joining us. And tell your friends that this is all recorded online, and so they can see the talks if they missed them today later. I'll stop recording now.
Thank you.